Introduction to Syntax Analysis. In this video, we are going to see about Introduction to Syntax Analysis. Syntax analysis is the second phase of the compiler. It gets the input from the tokens and generates a syntax tree or parse tree. Advantage of grammar for syntactic specification. A grammar gives a precise and easy to understand syntactic specification of a programming language. An efficient parser can be constructed automatically from a properly designed grammar. A grammar imparts a structure to a source program that is useful for its translation into object code and for the detection of errors. New constructs can be added to a language more easily when there is a grammatical description of the language. Role of the parser. In this video, we are going to see about the role of the parser. The parser or syntactic analyzer obtains a string of tokens from the lexical analyzer and verifies that the string can be generated by the grammar for the source language. It reports any syntax errors in the program. It also recovers from commonly occurring errors so that it can continue processing its input. Functions of parser. It verifies the structure generated by the tokens based on the grammar. It constructs the parse tree. It reports the errors. It performs error recovery. Issues. Parser cannot detect errors such as variable redeclaration, variable initialization before use, data type mismatch for an operation. The above issues are handled by semantic analysis phase. Syntax error handling. Programs can contain errors at many different levels. For example, lexical, such as misspelling a keyword. Syntactic, such as an arithmetic expression with unbalanced parentheses. Semantic, such as an operator applied to an incompatible operand. Logical, such as an infinitely recursive call. Functions of error handler. It should report the presence of errors clearly and accurately. It should recover from each error quickly enough to be able to detect subsequent errors. It should not significantly slow down the processing of correct programs. Error recovery strategies. The different strategies that a parse uses to recover from a syntactic error are panic mode, phrase level, error prediction, global correction. Panic mode recovery. On discovering an error, the parser discards input symbols one at a time until a synchronizing token is found. The synchronizing tokens are usually delimiters such as semicolon or end. It has the advantage of simplicity and does not go into an infinite loop. When multiple errors in the same statement are rare, this method is quite useful. Phrase level recovery. On discovering an error, the parser performs local correction on the remaining input that allows it to continue. Example: insert a missing semicolon or delete an extraneous semicolon, etc. Error predictions. The parser is constructed using augmented grammar with error predictions. If an error prediction is used by the parser, appropriate error diagnostics can be generated to indicate the erroneous constructs recognized by the input. Global correction. Given an incorrect input string X and grammar G, certain algorithms can be used to find a parse tree for a string Y such that the number of insertions, deletions, and changes of tokens is as small as possible. However, these methods are in general too costly in terms of time and space. Overview of context-free grammars. In this video, we are going to see about overview of context-free grammars. A context-free grammar is a quadruple that consists of terminals, non-terminals, start symbol, and productions. Terminals. These are the basic symbols from which strings are formed. Non-terminals. These are the syntactic variables that denote a set of strings. These help to define the language generated by the grammar. Start symbol. One non-terminal in the grammar is denoted as the start symbol, and the set of strings it denotes is the language defined by the grammar. Productions. It specifies the manner in which terminals and non-terminals can be combined to form strings. Each production consists of a non-terminal followed by an arrow, followed by a string of non-terminals and terminals. Example of context-free grammar. The following grammar defines simple arithmetic expressions. EXPR provides EXPR op EXPR. EXPR provide EXPR. EXPR provides minus EXPR. EXPR provides ID. Op provides plus. Op provides minus. Op provides multiplication. Op provides slash. Op provides higher precedence. In this grammar, ID plus minus multiplication slash higher precedence open bracket close bracket are terminals. EXPR op are non-terminals. Expression is the start symbol. Each line is a production. Derivations. two basic requirements for a grammar are to generate a valid string, to recognize a valid string. Derivation is a process that generates a valid string with the help of grammar by replacing the non-terminals on the left with the string on the right side of the production. Example: consider the following grammar for arithmetic expressions. E produce, E plus E, E into E, E minus E, ID. To generate a valid string minus of ID plus ID from the grammar, the steps are: E provides minus E, E provides minus of E, E provides minus of E plus E, E provides minus of ID plus E, E provides minus of ID plus ID. E is the start symbol. Minus of ID plus ID is the required sentence, that is only terminals. Strings such as E, minus of E are called sentinel forms. Types of derivations. The two types of derivation are leftmost derivation, rightmost derivation. In leftmost derivations, the leftmost non-terminal in each sentinel is always chosen first for replacement. In rightmost derivations, the rightmost non-terminal in each sentinel is always chosen first for replacement. Example: given grammar G, E provides E plus E, E into E, of E, minus E, ID. Sentence to be derived: minus of ID plus ID. Leftmost derivation: E provides minus E, E provides minus of E, E provides minus of E plus E, E provides minus of ID plus E, E provides minus of ID plus ID. String that appears in leftmost derivation is called left sentinel forms. Rightmost derivation: E provides minus E, E provides minus of E, E provides minus of E plus E into E, E provides minus of E plus ID, E provides minus of ID plus ID. String that appears in rightmost derivation is called right sentinel forms. Sentinels. Given a grammar G with start symbol S, if S provides alpha, where alpha may contain non-terminals or terminals, and then alpha is called the sentinel form of G. Yield or frontier of tree. Each interior node of a parse tree is a non-terminal. The children of node can be a terminal or non-terminal of the sentinel forms that are read from left to right. The sentinel form in the parse tree is called yield or frontier of the tree. Ambiguity. A grammar that produces more than one parse for some sentence is said to be ambiguous grammar. Example: given grammar G, E provides E plus E, E into E, of E, minus E, ID. The sentence ID plus ID into ID has the following two distinct leftmost: E provides E plus E, E provides ID plus E. E provides ID plus E into E. E provides ID plus ID into E. E provides ID plus ID into ID. E provides E into E. E provides E plus E into E. E provides ID plus E into E. E provides ID plus ID into E. E provides ID plus ID into ID. Categories of writing a grammar. In this video, we are going to see about categories of writing a grammar. There are 4 categories in writing a grammar. Regular expression versus context-free grammar. Eliminating ambiguous grammar. Eliminating left recursion. Left factoring. Each parsing method can handle grammars only of a certain form, hence, the initial grammar may have to be rewritten to make it parsable. The lexical rules of a language are simple and RE is used to describe them. Regular expressions provide a more concise and easier to understand notation for tokens than grammars. Efficient lexical analyzers can be constructed automatically from RE than from grammars. Separating the syntactic structure of a language into lexical and non-lexical parts provides a convenient way of modularizing the front end into 2 manageable sized components. Eliminating ambiguity. Ambiguity of the grammar that produces more than one parse tree for leftmost or rightmost derivation can be eliminated by rewriting the grammar. Consider this example. G statement provides if expression then statement, if expression then statement, else statement, other. This grammar is ambiguous since the string if E1 then if E2 then S1 else S2 has the following 2 parse trees for leftmost derivation. To eliminate ambiguity, the following grammar may be used. Statement provides matched statement, unmatched statement. Matched statement provides if expression, then matched statement, else matched statement, other. Unmatched statement provides if expression, then statement, if expression, then matched statement, else unmatched statement. Eliminating left recursion. A grammar is said to be left recursive if it has a non-terminal a such that there is a derivation a is equal to greater than a alpha for some string alpha. Top-down parsing methods cannot handle left recursive grammars, hence, left recursion can be eliminated as follows. If there is a production A provides A alpha, beta, it can be replaced with a sequence. A provides beta A dash provides alpha A dash epsilon. Without changing the set of strings derivable from A. Example, consider the following grammar for arithmetic expressions. E provides E plus T, T. T provides T into F, F provides E, ID. First eliminate the left recursion for E as E provides TE dash, E dash provides plus TE dash epsilon. Then eliminate for T as T provides FT dash, T dash provides multiplication FT dash epsilon. Thus, the obtained grammar after eliminating left recursion is E provides TE dash, E dash provides plus TE dash epsilon, T provides FT dash, T dash provides multiplication FT dash epsilon, F provides E, ID. Algorithm to eliminate left recursion. Arrange the non-terminals in some order A1, A2 up to AN. For I is equal to 1 to n, do begin. For j is equal to 1 to I minus 1, do begin. Replace each production of the form AI provides AJ gamma by the productions AI provides del 1 gamma, del 2 gamma up to del k gamma, where AJ provides del 1, del 2 up to del k are all the current AJ productions. And eliminate the immediate left recursion among the AI productions. End. Left factoring. Left factoring is a grammar transformation that is useful for producing a grammar suitable for predictive parsing. When it is not clear which of two alternative productions to use to expand a non-terminal A, we can rewrite the A productions to defer the decision until we have seen enough of the input to make the right choice. If there is any production A provides alpha beta 1, alpha beta 2, it can be rewritten as A provides alpha A dash provides beta 1, beta 2. Consider the grammar G. S provides IETS, IETSES, A. E provides B. Left factored, this grammar becomes S provides IETSS dash A. S dash provides ES epsilon. E provides B. Introduction to parsing. In this video, we are going to see about introduction to parsing. Parsing is the process of analyzing a continuous stream of input in order to determine its grammatical structure with respect to a given formal grammar. Types of parsing. Bottom-up parsing, top-down parsing. Top-down parsing can be viewed as an attempt to find a leftmost derivation for an input string or an attempt to construct a parse tree for the input starting from the root to the leaves. Types of top-down parsing. Predictive parsing, recursive descent parsing. Recursive descent parsing. In this video, we are going to see about recursive descent parsing. Recursive descent parsing is one of the top-down parsing techniques that uses a set of recursive procedures to scan its input. This parsing method may involve backtracking, that is, making repeated scans of the input. Example for backtracking. Consider the grammar G. S provides CAD. A provide AB, A. And the input string W is equal to CAD. The parse tree can be constructed using the following top-down approach. Step 1. Initially create a tree with single node labeled S. An input pointer points to C, the first symbol of W. Expand the tree with the production of S. Step 2. The leftmost leaf C matches the first symbol of W, so advance the input pointer to the second symbol of W, A, and consider the next leaf A. Expand A using the first alternative. Step 3. The second symbol A of W also matches with second leaf of tree, so advance the input pointer to third symbol of W, D, but the third leaf of the tree is B, which does not match with the input symbol D. Hence, discard the chosen production and reset the pointer to second position. This is called backtracking. Step 4. Now, try the second alternative for A. Now we can halt and announce the successful completion of parsing. Example for recursive descent parsing. A left recursive grammar can cause a recursive descent parser to go into an infinite loop. Hence, elimination of left recursion must be done before parsing. Consider the grammar for arithmetic expressions. E provides E plus T, T. T provides T into F, F. F provides E, ID. After eliminating the left recursion, the grammar becomes E provides TE dash, E dash provides plus TE dash epsilon, T provides FT dash, T dash provides multiplication FT dash epsilon, F provides E, ID. Now we can write the procedure for grammar as follows. Recursive procedure. Predictive parsing. In this video, we are going to see about predictive parsing. Predictive parsing is a special case of recursive descent parsing where no backtracking is required. The key problem of predictive parsing is to determine the production to be applied for a non-terminal in case of alternatives. Non-recursive predictive parser. The table-driven predictive parser has an input buffer, stack, a parsing table, and an output stream. Predictive parsing program. The parser is controlled by a program that considers X, the symbol on top of stack, and A, the current input symbol. These two symbols determine the parser action. There are three possibilities. If X is equal to A is equal to $, the parser halts and announces successful completion of parsing. If x is equal to a not equal to $, the parser pops x off the stack and advances the input pointer to the next input symbol. If x is a non-terminal, the program consults entry m of x, a of the parsing table m. This entry will either be an X production of the grammar or an error entry. If m of x, a is equal to x provides UVW, the parser replaces x on top of the stack by WVU. If m of x, a is equal to error, the parser calls an error recovery routine. Algorithm for non-recursive predictive parsing. Input: a string W and a parsing table M for grammar G. Output: if W is in L of G, a leftmost derivation of W, otherwise an error indication. Method: initially the parser has $S on the stack with S, the start symbol of G on top, and $W in the input buffer. The program that utilizes the predictive parsing table M to produce a parse for the input is as follows. Procedure: algorithm for non-recursive predictive parsing. Set IP to point to the first symbol of $W. Repeat: let X be the top stack symbol and A the symbol pointed to by IP. If X is a terminal or $, then if X is equal to A, then pop X from the stack and advance IP. Else error, open close bracket. Else X is a non-terminal. If m of x, a is equal to x provides y1, y2 up to yk, then begin. Pop x from the stack. Push yk, yk minus 1, up to y1 onto the stack with y1 on top. Output the production x provides y1, y2 up to yk. End. Else error, open bracket close bracket. Until x is equal to $, stack is empty. Predictive parsing table construction. The construction of a predictive parser is aided by two functions associated with a grammar G. First, follow. Rules for first, open close bracket. If x is terminal, then first of x is x. If x provides epsilon is a production, then add epsilon to first of x. If x is non-terminal and x provides a alpha is a production, then add a to first of x. If x is non-terminal and x provides y1, y2 up to yk is a production, then place a in first of x if for some I. A is in first of yi and epsilon is in all of first of y1 up to first of yi minus 1, that is y1 up to yi minus 1 provides epsilon. If epsilon is in first of yj for all j is equal to 1, 2 up to k, then add epsilon to first of x. Rules for follow. If S is a start symbol, then follow of S contains $. If there is a production A provides alpha B beta, then everything in first beta except epsilon is placed in follow of B. If there is a production A provides alpha B or a production A provides alpha, b, beta, where first of beta contains epsilon, then everything in follow of A is in follow of B. Algorithm for construction of predictive parsing table. Input grammar G, output parsing table M. Method. For each production A provides alpha of the grammar. Do steps 2 and 3. For each terminal A in first of alpha, add A provides to alpha to M of A, A. If epsilon is in first of alpha, add A provides alpha to M of A, B for each terminal B in follow of A. If epsilon is in first of alpha and dollar is in follow of A, add A provides alpha to M of A, dollar. Make each undefined entry of M be error. Example. Consider the following grammar. E provides E plus T, T. T provides T into F, F. F provides E, ID. After eliminating left recursion, the grammar is E provides TE dash. E dash provides plus TE dash epsilon. T provides FT dash. T dash provides into FT dash epsilon. F provides E, ID. First of E is equal to ID. First of E dash is equal to plus epsilon. First of T is equal to ID. First of T dash is equal to into epsilon. First of F is equal to ID. Follow of E is equal to dollar. Follow of E dash is equal to dollar. Follow of T is equal to plus dollar. Follow T dash is equal to plus dollar. Follow F is equal to plus into dollar. Predictive parsing table. Stack implementation. LL of 1 grammar. The parsing table entries are single entries. So each location has not more than one entry. This type of grammar is called LL of 1 grammar. Consider this following grammar. S provides IETS, IETSES, A. E provides B. After eliminating left factoring, we have S provides IETSS-A. S dash provides ES epsilon. E provides B. To construct a parsing table, we need first and follow for all the non-terminals. First of S is equal to I, A. First of S dash is equal to E, epsilon. First of E is equal to B. Follow of S is equal to dollar, E. Follow of S dash is equal to dollar, E. Follow of E is equal to T. Parsing table. Since there are more than one production, the grammar is not LL of 1 grammar. Actions performed in predictive parsing. Shift, reduce, accept, error. Implementation of predictive parser. Elimination of left recursion, left factoring and ambiguous grammar. Construct first and follow for all non-terminals. Construct predictive parsing table. Parse the given input string using stack and parsing table. Overview of bottom-up parsing. In this video, we are going to see about overview of bottom-up parsing. Constructing a parse tree for an input string beginning at the leaves and going towards the root is called bottom-up parsing. A general type of bottom-up parser is a shift-reduce parser. Shift-reduce parsing. Shift-reduce parsing is a type of bottom-up parsing that attempts to construct a parse tree for an input string beginning at the leaves, that is the bottom, and working up towards the root, that is the top. Example: consider the grammar S provides A, B, E. A provides A, B, C, B. B provides D. The sentence to be recognized is A, B, B, C, D, E. A, B, B, C, D, E. A provides B. A, B, C, D, E. A provides A, B, C. A, D, E. B provides D. A, B, E. S provides A, B, E. S provides A, B, E. Provides A, D, E. Provides A, B, C, D, E. Provides A, B, B, C, D, E. The deductions trace out the rightmost derivation in reverse. Handles. A handle of a string is a substring that matches the right side of a production and whose reduction to the non-terminal on the left side of the production represents one step along the reverse of a rightmost derivation. Example: given grammar G, E provides E plus E, E into E, of E, ID. And the input string ID 1 plus ID 2 into ID 3. Rightmost derivation E provides E plus E. Provides E plus E into E. Provides E plus E into ID 3. Provides E plus ID 2 into ID 3. Provides ID 1 plus ID 2 into ID 3. Handle pruning. A rightmost derivation in reverse can be obtained by handle pruning, that is, if W is a sentence or string of the grammar at hand, then W is equal to gamma n, where gamma n is the nth right sentinel form of some rightmost derivation. Stack implementation of shift-reduce parsing. Actions in shift-reduce parser. Shift: the next input symbol is shifted onto the top of the stack. Reduce: the parser replaces the handle within a stack with a non-terminal. Accept: the parser announces successful completion of parsing. Error: the parser discovers that a syntax error has occurred and calls an error recovery routine. Conflicts in shift-reduce parsing. There are two conflicts that occur in shift-reduce parsing. Shift-reduce conflict. Reduce-reduce conflict. Shift-reduce conflict. Example: consider the grammar E produce E plus E, E into E, ID and input ID plus ID into ID. Reduce conflict. Example: consider the grammar M provides R plus R, R plus C produce C, and input C plus C. Viable prefixes. Alpha is the viable prefix of the grammar if there is W such that alpha W is a right sentinel form. The set of prefixes of right sentinel forms that can appear on the stack of a shift-reduce parser are called viable prefixes. The set of viable prefixes is a regular language. Constructing shift-reduce parsing. In this video, we are going to see about constructing shift-reduce parsing. An efficient way of constructing shift-reduce parser is called operator precedence parsing. Operator precedence parser can be constructed from a grammar called operator grammar. These grammars have the property that no production on right side is epsilon or has two adjacent non-terminals. Example: consider the grammar E provides EAE, E minus E ID. A provides plus modulus of minus into modulus of slash higher precedence. Since the right side EAE has a three consecutive non-terminals, the grammar can be written as follows: E provides E plus E, E minus E, E into E, E slash E, E high precedence E, minus E, ID. Operator precedence relations. There are three disjoint precedence relations, namely less than, equal to, greater than. The relations give the following meaning: A less than dot B minus A yields precedence to B. A is equal to B minus A has the same precedence as B. A dot greater than B minus A takes precedence over B. Rules for binary operations. If operator theta 1 has higher precedence than operator theta 2, then make theta 1 dot greater than theta 2 and theta 2 lesser than dot theta 1. If operators theta 1 and theta 2 are of equal precedence, then make theta 1 dot greater than theta 2 and theta 2 dot greater than theta 1 if operators are left associative. Theta 1 lesser than dot theta 2 and theta 2 lesser than dot theta 1 if right associative. Make the following for all operators theta. Theta lesser than dot id, comma id dot greater than theta. Theta lesser than dot, comma lesser than dot theta. Dot greater than theta, comma theta dot greater than. Theta dot greater than dollar, dollar lesser than dot theta. Also make is equal to, comma lesser than dot, comma dot greater than, comma lesser than dot id, comma id dot greater than, comma dollar lesser than dot id, comma id dot greater than dollar, comma dollar lesser than, comma greater than dollar. Example: operator precedence relations for the grammar. E provides E plus E, E minus E, E into E, E slash E, higher precedence E, E minus E, ID is given in the following table assuming is highest precedence and right associative. Multiplication and division are of next higher precedence and left associative, and plus and minus are of lowest precedence and left associative. Note that the blanks in the table denote error entries. Operator precedence parsing algorithm. Input an input string W and a table of precedence relations. Output, if W is well formed, a skeletal parse tree with a placeholder non-terminal E labeling all interior nodes, otherwise an error indication. Method: initially the stack contains $, and the input buffer the string W $. To parse, we execute the following program. Stack implementation of operator precedence parsing. Operator precedence parsing uses a stack and precedence relation table for its implementation of above algorithm. It is the shift-reduce parsing containing all four actions: shift, reduce, accept, and error. The initial configuration of an operator precedence parsing is stack $input W$, where W is the input string to be parsed. Example: consider the grammar E provides E plus E, E minus E, E into E, E divided by E, E higher precedence E, ID. Input string is ID plus ID into ID. The implementation is as follows. Advantages of operator precedence parsing. It is easy to implement. Once an operator precedence relation is made between all pairs of terminals of a grammar, the grammar can be ignored. The grammar is not referred anymore during implementation. Disadvantages of operator preceding parsing. It is hard to handle tokens like the minus sign, which has two different precedents. Only a small class of grammar can be parsed using operator precedence parser. LR parsing algorithm. In this video, we are going to see about LR parsing algorithm. LR parsing algorithm, an efficient bottom-up syntax analysis technique that can be used to parse a large class of CFG is called LR of K parsing. The L is for left to right scanning of the input, the R for constructing a rightmost derivation in reverse, and the K for the number of input symbols. When K is omitted, it is assumed to be 1. Advantages of LR parsing. It recognizes virtually all programming language constructs for which CFG can be written. It is an efficient, non-backtracking shift-reduce parsing method. A grammar that can be parsed using LR method is a proper superset of a grammar that can be parsed with predictive parser. It detects a syntactic error as soon as possible. Drawbacks of LR method. It is too much of work to construct a LR parser by hand for a programming language grammar. A specialized tool called a LR parser generator is needed. Example, YACC. Types of LR parsing method. SLR, simple LR. CLR, canonical LR. LALR, look ahead LR. The LR parsing algorithm. It consists of an input, an output, a stack, a deliver program, and a parsing table that has two parts, that is action and goto. The driver program is the same for all LR parser. The parsing program reacts characters from an input buffer one at a time. The program uses a stack to store a string of the form S0 into 1S1 into 2S2 up to XM/SM, where SM is on top. Each XI is a grammar symbol and each SI is a state. The parsing table consists of two parts, action and goto function. Action. The parsing program determines SM, the state currently on top of stack, and AI, the current input symbol. If then consults action, that is SM, AI, in the action table, which can have one of four values. Shift S, where S is a state. Reduced by a grammar production, A provides beta. Accept and error. Goto. The function goto takes a state and grammar symbol as arguments and produces a state. LR parsing algorithm. Using ambiguous grammars. In this video, we are going to see about the using of ambiguous grammar. Ambiguous, then it creates the conflicts and we cannot parse the input string with such ambiguous grammar. But for some languages in which arithmetic expressions are given, ambiguous grammar are most compact and provide more natural specification as compared to equivalent unambiguous grammar. Secondly, using ambiguous grammar, we can add any new productions for special constructs. While using ambiguous grammar for parsing the input string, we will use all the disambiguating rules so that each time only one parse tree will be generated for that specific input. Thus, ambiguous grammar can be used in controlled manner for parsing the inputs. We will consider some ambiguous grammar and let us try to parse some input string. Using precedence and associativity to resolve parsing action conflicts. In this video, we are going to see about using precedence and associativity to resolve parsing action conflicts. Consider an ambiguous grammar for arithmetic expression. E provides E plus E, E provides E into E, E provides E, E provides ID. Now we will build the set of LR of 0 items for this grammar. Here follow of E is equal to plus comma dot comma dollar. We have computed follow E as it will be required while processing. Now, using the same rules of building SLR of 0 parsing table, we will generate the parsing table for above set of items. As we can see in the parsing table, the shift or reduce conflicts occur at the states 7 and 8. We will try to resolve it. How? Let us consider one string ID plus ID into ID. Has into has precedence over plus, we have to perform multiplication operation first, and for that it is necessary to push into on the top of the stack. By this we can perform E into E first and then E plus E. Therefore, as you can see in the above table of parsing conflict can be resolved by assigning shift operation. Hence action 7 comma multiplication is equal to S5. Similarly, if we consider the input ID into ID plus ID dollar for processing, the conflict in action of 8 comma plus is equal to S4 or R2 can be resolved by allowing R2 action, as we have to perform E into E operation first and then ID into ID dollar strings. You can see that the conflicts for action 7 comma plus and action of 8 comma into can be resolved respectively. The resolution is action 7 comma plus is equal to R1 and action 8 comma into is equal to R2. Finally, the ambiguous grammar without T, any conflict has following SLR parse table as using dangling else ambiguity. In this video, we are going to see about using dangling else ambiguity. Consider the grammar. S provides ISES ISA, where ISES is equal to if expression then statement else statement. IS is equal to if expression then statement. A is equal to all other productions. We will have this grammar in this manner. S dash provides S. S provides ISES, ISA. Now we will build the LR of 0 set of items for S. The follow of S is equal to E, $. Now we will build the SLR parse table for above obtained set of items. Clearly in the above table at action 5, E, there is a shift or reduce conflict. We will now try to resolve it. Consider the input $AEA for processing. That means the choice of R2 in action 4, E is not valid. Hence, we will try it by choosing the shift action. Logically also, we should favor the shift operation, as by shifting the else, we can associate it with previous if expression then statement. Therefore, shift or reduce conflict is resolved in favor of shift. Thus, by resolving the conflict, we get the parsing table for dangling else problem as parser generators. In this video, we are going to see about parser generators. We have discussed the manual method of construction of LR parser. This involves a lot of work for parsing the input string. Hence, there is a need for automation of this process in order to achieve the efficiency in parsing the input. Certain automation tools for parser generation are available. YACC is one such automatic tool for generating the parser program. YACC stands for Yet Another Compiler, which is basically the utility available from Unix. Basically, YACC is LALR parser generator. The YACC can report conflicts or ambiguities, if at all, in the form of error messages. First, we write a YACC specification file. Let us name it as x.y. The file is given to the YACC compiler by Unix command YACC_x.y. Then it will generate a parser program using your YACC specification file. This parser program has a standard name as y.tat.c. This is basically parser program in C generated automatically. We can also give the command with -d option YACC-d x.y. YACC specification. In this video, we are going to see about YACC specification. First of all, we will see the structure of YACC specification. The YACC specification file consists of three parts: declaration section, translation rules section, and supporting C functions. The specification file with these sections can be written as %open bracket, declaration section, %, close bracket, %, translation rules section, %, required C functions, declaration part, In this section, ordinary C declarations can be put. Not only can this have, we also declared grammar tokens in this section. The declaration of tokens should be after percentage. Translation rules. The translation rules section consists of all the production rules of context-free grammar with corresponding actions. For instance, Rule 1, Action 1. Rule 2, Action 2. Rule N, Action N. If there are more than one alternative to a single rule, then those alternatives should be separated by character. The actions are typical C statements. If CFG is LHS provides alternative 1, alternative 2 up to alternative N, then LHS alternative 1 action 1, alternative 2 action 2 up to alternative N action N. C function section. This section consists of one main function in which the routine YY parse will be called, and it also consists of required C functions. Programming example. Write a YACC program for implementing desktop calculator. Program. We will first create Lex program named calc.I. Then we will write program for YACC as calc.y. The extension to Lex program is .I and to YACC program is .y. Lex program. The YACC program. In this video, we are going to see about YACC program. Program. Compiling and running of Lex and YACC programs. The output of the program can be obtained by following commands on Unix shell. Root @localhost #lexcalc.l. By this command, lex.yy.c will be created. Root @localhost #yacc.d.calci.y. By this command, y.tab.c will be created. Root @localhost #cc y.tab.c lex.yy.cll.ly.lm. By this command, both Lex and YACC generated C programs will be compiled. Enter the expression 2 plus 2, answer is equal to 4. 2 into 2 plus 5 by 4, answer is equal to 5.25. MEM is equal to cos 45. Sin 45 by MEM. Answer is equal to 1. ln 10. Answer is equal to 2.30259. Explanation of program. Declaration part. Percentage token is used to declare tokens in the YACC. In the above program, token number can be declared as percentage token dval number. The precedence and associativity can be declared in the above program. %left, %right, and %non-associative declares the associativity of the operator being left associative, right associative, or non-associativity respectively. The precedence can be declared in an increasing order. The YYL variable used is the union of type double. YACC can associate data type with the token by using this YYL variable, %token dval number. It means token number has the data type double. Any number of data types can be declared in union. The operators on the same line have equal precedence. For instance, plus and minus has the same precedence. Rule section. In the rule section is used to separate LHS and RHS of production rule. The termination of each rule is given by semicolon. The $$ is used as attribute value at LHS of the grammar. If there is a rule E plus E, then it has attribute values as $1 plus $3. Since E is equal to $1, plus is reserved for $2 and E is equal to $3. To represent the RHS of the grammar, $1, $2 up to $n symbols are used. Finally, the answer can be in $$ is equal to $1. Subroutine section. In the main important function, YYParse is called YACC invokes first YYParse, which in turn calls YYLex when it requires tokens. The routine YY error is used to print the error message when an error is occurred in parsing of input. Thus, we have seen how an input string is parsed and syntactically checked.